as a continuation of our discussion of the meaning and application of singularity functions. Let me take an example. Suppose you are given this function f of t, which has a discontinuity here and also has discontinuous derivative and so on. F of t is described like this. Now, what is, if f of t is like this, what is the meaning of f of t ut? So, this function is being multiplied by u of t. That means, the negative values of the function for negative values of t are cut off, and for positive values of t it is multiplied by 1. Therefore, f of t ut would be the reproduction of the same curve for positive values of time. For negative values of time it is 0. So, this is exactly what will be f of t ut. If this is f of t, is f of t ut where the section for the negative values of time is cut off. Now, suppose on the other hand, if this is f of t, I want to know what is f of t minus 1 ut. If this is f of t minus 1 is a curve which is delayed by 1 second. Therefore, it will have this curve, this is minus 1, and this break point occurs at 3 units, and this is f of t minus 1. And f of t minus 1 multiplied by u of t, f of t minus 1 has values only for positive t, multiplied by u of t will not disturb this. Therefore, this will be f of t minus 1 u of t. On the other hand, if I multiply f of t by u of t minus 1, what will be the result? If I multiply f of t by u of t minus 1, I have u of t minus 1 is a step starting at plus 1. So, at this point the step starts, and then you are multiplying this curve by u of t minus 1. Therefore, you have at 1 the curve will be reproduced from t equals 2 onwards only. That means, this portion of the curve gets cut off, truncated. So, that is, you see the notation f of t ut, f of t minus 1 ut, f of t ut minus 1. So, this is how you can understand the meanings of the various functions of time. Whenever u of t minus 1 means it starts from t equals 1 onwards, and you should be able to get have the ability to recognize the waveforms which when the f of t is multiplied by step functions with the delayed step functions and so on and so forth. Let me take now, we have seen 3 functions now, u of t, the ramp function rt, and the delta function delta t. How are they interrelated? You see that if I differentiate u of t, I get delta t. Delta t is d by dt of ut. Because when you differentiate, this derivative is 0 here and here. At this point, the sudden jump of 1 unit, and the area under this delta curve is 1 unit. That means, when you integrate through the delta, you get a rise of 1 unit. Therefore, u of t is the integral of delta t, and delta t is the derivative of u of t. So, u of t can be written as from minus infinity to t delta t dt. So, that is how these two are related. In a similar fashion, suppose you have rt, you take the derivative, you get the step function. If you integrate ut, you get the ramp function. So, d by dt of rt is the unit step function, and integral from minus infinity to t of u of t dt is the ramp function. That means, starting with the ramp, you take the derivative, you get this, you take the derivative, you get this. Or starting from the impulse, you take the integral, you get u of t, you take the integral of that, you get r of t. So, these are the 3 are interrelated in this fashion. So, using this, let me take an example. Suppose I have a 4 volts DC source and connect this to a 2 farad capacitor at t equals 0. I would like to find an expression for the current in the circuit. Right. you can see that initially the capacitor voltage is 0. Let us say Vc 0 minus before the switch is closed is equal to 0. The capacitor is uncharged. As soon as you close the switch, the capacitor by Kirchhoff's voltage law must acquire a voltage of 4 volts. No way you can avoid it, even though the capacitor voltages you say are continuous in the normal course of things, but here according to the rules of the game, when you close the switch, this 4 volts must appear across the capacitor. So the capacitor voltage to before t equals 0 is 0, immediately after that it must jump to 4 volts. That means 8 coulombs of charge must be dumped on the capacitor in 0 time. So the charge in the capacitor at t equals 0 minus is 0, at t equals 0 plus but it is 8 coulombs. So 8 coulombs must be dumped on the capacitor in no time at all in the interval from 0 minus to 0 plus. That means the current must be infinite, but the area under the curve of the current waveform, which is really the charge, must be 8 units. So you can obviously see that the current in the circuit is described by a delta function. So the current in the circuit I of t can be written as 8 delta t. So because the area under this curve is 8 units, that is represents the charge that has been put on the capacitor in infinitesimal interval between 0 minus to 0 plus. So I of t is 8 delta t. You can arrive at this result in a more formal way. Of course, we have physically argued that this should be the answer, but you can say that the capacitor voltage Vc, what is the expression for the capacitor voltage? For time t less than 0 it is 0, for time t greater than 0 it is 4 volts once you close the switch. Therefore, Vc can be written as 4 ut. That is the voltage waveform across the capacitor. It will be like this. We know that the current in a capacitor is C dV C dt. I equals C dV C dt. That is the basic equation, the terminal relation for a capacitor. Now in this case the capacitor is 2 farads, therefore 2 times 4 times d by dt ut. That is the expression for the current, and we have just now observed d by dt of ut is delta t, therefore this is 8 delta t. So if you look at the waveform of the current in the capacitor, it is a delta of 8 units magnitude sitting at the horizon. That is the expression for the current in the capacitor. Let me take a second example. We have a voltage source Vs connected to a resistor capacitor combination. The capacitor is 2 farads, let the current be I here. So let in this circuit we know the waveform of Vc and we are asked to find out Vs. So let Vc be in this circuit be having a waveform like this. So this is a triangular pulse T, this is 2 volts. So we are given this waveform, the function for the expression or the waveform for Vc, and we are asked to find out Vs. How do we go about it? Now let us first find an expression for Vc. The plan of attack is once you find an expression for Vc, C dV C dt will give me the expression for the current. You add the voltage across the resistance plus the voltage across the capacitance, and that will give me the value of Vs. That is how I proceed. So how do we find the expression for Vc? It is 0 up to t equals 0 and then starts with a ramp which has a slope of 2 units, 2 volts in 1 second. Therefore, 2 RT would be an expression like this. At this point, first of all, the ramp, the rate of growth must be arrested at this point, which was earlier increasing. Therefore, you must introduce a negative ramp of 2 units of magnitude starting at t equals 1. Now, if you had only these 2 ramps, then you will have a growing ramp like this. At this time, this growth is arrested by a negative ramp and the curve would have continued like that. If you add these 2, you would observe that the resultant of these 2 would be something like this. But then we would like to bring this down to 0. So you must introduce a negative step of unit magnitude starting at t equals 1 in order to pull this down to 0, which means you must introduce in further a 2 ut minus 1. So, the sum of these three quantities will describe this triangular pulse, that is your Vc. Therefore, the current in this is C dV C dt, and C is 2 farads. So, 2 times the derivative of these expressions, 2 RT, the derivative of that would be 2 ut minus 2 RT minus 1, the derivative of this 2 times u of t minus 1, the derivative of ramp function is the step function, and then minus 2 times the derivative of a step function is an impulse function. So, delta t minus 1, that is your I, and Vs equals Vc plus R times I, which is equal to 1. Therefore, Vc plus I, the sum of these two Vc plus I will give me the value of the Vs. Therefore, you have combining these two 4 ut, 4 ut here plus 2 RT, this one, minus 4 ut minus 1 from this, minus 2 RT minus 1 from this one, 1 minute, minus 4 RT minus 4 ut minus 1, there is another 2 ut minus 1, therefore, I must write here 6 ut minus 1, 6 ut minus 1 minus 2 RT minus 1, and then in addition you have minus 4 delta t minus 1. That is the expression for this 4 ut plus 2 RT minus 6 ut minus 1 minus 2 RT minus 1 minus 4 delta t minus 1, that is your Vs. If you plot this, Vs would have a waveform like this. To start with 4 ut, so it starts with 4. It is 0 for negative values of time, and at that point of time it has a ramp with a slope of 2 units. So, it is going on increasing right up to t minus 1, t equal t right up to 1. So, up to 1 this will build up to a value of 6 volts up to 1. At this point of time you have a negative going ramp of 2 units. Therefore, it means that whatever was increasing earlier is now pulled down by the same slope. That means, if you added this function it would have continued like this, but you also have a step of minus 6. So, instead of remaining constant here, this would continue, this will come down here by 6 units. Therefore, the sum of these first 4 terms 4 ut 2 RT 6 ut minus 1 minus 2 RT minus 1 would have been just like this. This would have been the result, but we also have a delta function of minus 4 units here. So, in addition to this you have a delta function of minus 4 units. So, that would be the shape of the Vs curve. So, all this expression describes this particular waveform. So, you observe now that whenever you have waveforms of this type with discontinuities and discontinuous derivatives, one can use the singularity functions with advantage to describe the corresponding waveforms. And in fact, in all this discussion we did not have to say this is the expression for t equals less than 0, this is the expression for t between 0 and 1, this is the expression for t greater than 1. We have one single expression valid for the entire range, and this constitutes the central advantage of describing these functions with the help of singularity functions.